So we're going to talk about a theoretical computer science lens on consciousness. And again, this is joint work with Manuel and also Avrim Blum, who's our in-house machine learning expert. And okay. And so I'm not sure who the audience is, but I'm going to just start very generally at first. So what is consciousness? Throughout the millennia, consciousness has been the purview of philosophers and theologians. Until about 35 years ago, the scientific study of consciousness was taboo. Now it's actively pursued also by cognitive scientists, neuroscientists, psychologists, AI researchers, physicists, and mathematicians. So what changed? Well, as many of you know, in 1990, the fMRI technology was developed, which allowed neuroscientists to look at the brain non-invasively. And also, Dan Dennett came out with his blockbuster book, Consciousness Explained, which gives a functionalist or maybe a computationalist perspective on consciousness. And then a few years later, Francis Crick comes out with his book, The Astonishing Hypothesis, which actually advocated the scientific study of consciousness, which really was the main thing that took it out of the taboo for scientific studies. And in fact, what he was advocating was looking at neural correlates of consciousness. And then about the same time, the philosopher David Chalmers' book, The Consciousness Mind, introduced the hard problem. So let me just talk about the hard and easy problems of consciousness, a la David Chalmers. Chalmers says the easy problems of consciousness are those that seem directly susceptible to the standard methods of cognitive science, whereby a phenomenon is explained in terms of computational neuromechanisms. This is often called functional or access consciousness. And in our model, what we're going to do is call this something like this conscious attention. And the hard problem, according to Chalmers, is that the really hard problem of consciousness is the problem of experience. When we think and perceive, there is a whir of information processing, but there is also a subjective aspects, and this is often called subjective or phenomenal consciousness, and in our model, we call it conscious awareness. And it's usually associated with the word qualia, the feeling of what is it like, the feeling of what it's like to be a bat. Many focus on what it feels like when you see red. And many view the hard problem as needing a new kind of science to explain subjective consciousness. And we view the hard problem as a challenge to show that subjective consciousness is actually computational. So let me go to theoretical computer science. This is a branch of mathematics that studies computation given limited resources, limited time, limited space. And it differs from the classical Turing theory, which assumes these resources are unbounded. And mathematics differs from other methods used in science. It abstracts, it formalizes informal notions, it proposes axioms, and then it sees what happens. It derives results, theorems. So what we'd like to do is construct a simple formal mathematical model that at a high level exhibits and explains phenomena associated with human consciousness, aligns with and integrates underlying principles of major theories of consciousness, and answers questions that a theory of consciousness should encompass. Okay, so what I'm going to do is describe the conscious Turing machine, which is inspired in part by Alan Turing's simple yet powerful model of computation. And here we have a 23-state universal Turing machine that can compute any computable function. And what that means is what you can compute in the cloud or a supercomputer, or even in ChatGPT, what you can compute, you could actually already compute in a universal Turing machine. And we're also inspired by Bernard Barr's global workspace theory of consciousness, his theater model. And one of the reasons here is, so with Turing, what we like is that there's a simple model that explains a lot. And what we like about Barr's is that his model really looked amenable to actually formalizing mathematically. So let me show you what Barres's model is. So for Barres, consciousness is the activity of actors in the play performing on a stage of working or short-term memory, and their performance is under observation by a huge audience of powerful unconscious processes in long-term memory that are sitting in the dark. And the unconscious processors, those in the audience, vie amongst themselves to get their script or their query or information on stage so it can be broadcast to the audience. So let me give you what we give often as our example of the theater model in action. And many of people have had this experience. You're at a party, you see someone that you know, but for the life of you, you can't remember her name. And then you're sort of driving home, and on the way home or when you get home, her name pops up. Too late to do anything about it. So what's going on? So one of your processors in the audience is so embarrassed that you can't remember her name that it sends up to the stage a message, what's her name, that gets on stage and gets broadcast. So then again, another processor might recall where you first met, maybe in a computer science class. It gets up onto stage, gets broadcast, something about what she does. She's a machine learning AI person, gets up there and it gets broadcast. Another processor says her name begins with N, gets broadcast. But a half hour later, her name Tina comes up to the stage, to the conscious short-term memory from the audience, the unconscious long-term memory processors, which have been thinking, searching. Now, if you notice in my example here, Tina does not jibe with N, and we'll get to that in a minute, what happened there. But the conscious self on stage is not privy to that working of the unconscious self going on. So before we go ahead, I want to say a few words about what the conscious Turing machine is not. It's not a standard Turing machine. So what gives the CTM its feeling of consciousness, it's not its input-output map, nor its computing power, but it's what's under the hood, and that's what we'd like to talk about. And it's not a standard global workspace model either. It's a formal mathematical model. It has a well-defined competition for those processors to get their information on stage. I mean, in terms of Barres or others, they just discuss amongst themselves and decide. We have a well-defined competition. And also, unlike practically all global workspace models we've seen, there is no central executive in the CTM. And that actually makes it a good model for an AGI. Talk a little bit about that. And subjective feelings of consciousness will arise in the CTM from the co-evolution of brainish, which is CTM's self-generated multimodal internal language and its model of the world. And I'll try to talk about that also. And finally, the CTM is not a model of the brain. It's way too simple for that. Okay, so here's an outline of our talk. We'll first give an overview of the CTM model, which one can think of as a framework for or high-level specifications for the model, and then go ahead to talk about the conscious attention in CTM, which is our version of access consciousness, and conscious awareness in the CTM, which is our version of subjective consciousness. And that part will depend on the co-evolution of brainish and the model of the world. So here I'll give a formal structure for CTM. It's a 7-tuple, has STM, LTM, uptree, downtree links, input, output. Time is measured in discrete clock ticks, t equals 0, all the way up to maybe 10 to the 10th clicks. CTM is born at time 0, and it has a finite lifetime. And then we have lots of specifications for these various, or definitions for these various components, which I will not give you, but I will now give a cartoon or a high-level picture. So here's our CTM. We start with a very tiny short-term memory. That's our stage. And the stage can hold one chunk of information. So that's not the 7 plus or minus 2 chunks that is usually thought of as what the short-term memory can hold, but we're only looking for simplicity, and one chunk will do. And then we have many, very huge number of long-term memory processors. This is our audience. These are powerful processors, and we're assuming we have maybe more than 10 to the 7th or about 2 to the 24th of these processors. We think of them as random access machines. And 10 to the 7th is the number of cortical columns in the brain. And so we're sort of looking a little bit larger than that. Okay. And for simplicity, all of our processes will be in LTM. We don't have any other special places for processors. The short-term memory is not a process. All the processes are in long-term memory are in the audience. And we can simplify things and put everything there. And to start, all long-term memory processes are unlinked and they're independent when the CTM is born. But built into all long-term processes are some initial properties. There's some predictive learning algorithms, and one important one is the sleeping experts algorithm of Avrim Blum. And let me just say what that is in terms of what's her name. So remember, one of the processors said her name started with N, but actually it turned out her name was Tina. So the processor that said her name started with N, its sleeping expert algorithm will say, hey, you were a little too bold. You put too much weight on your thought that her name started with M. It got up on the stage, but you were way too bold. So how about the next time cooling it, lower the weights you give your chunks, the information. But there might be another processor that actually said her name started with T, but did not give enough weight to that information, so it didn't get up on stage. So its sleeping expert algorithm said, hey, after a while, you were right. Her name was Tina, but you should be not so timid. Give a little bit more weight to your information in the future. So the sleeping expert algorithm really helps adjust the weights that processors give their information. Most of the processors are generic, but there are some built-in processors. So we have input or like sensory processors that deal with the input information that's coming from the outside world. We have output processors that activate actuators, such as motor processors would actuate legs or moving components. And we also have gauge processors, which you can think of as homeostats. So maybe an oxygen processor, how much oxygen it's getting or fuel it's getting, fuel gauge. But all other processors then will start off generically. Okay. And each processor has its own internal language, but processors communicate within CTM in brainish, and that's CTM's self-generated multimodal language. So let me say a couple of words about this. As some of the things about the CTM we built in from the start, but others came because we needed a language. We needed a language that processes could use to communicate with each other. So that's how brainish came out. And when we first looked at brainish, we were actually looking at a little bit of how machine learning people were looking at multimodal languages, but they were using huge dimensional spaces. They didn't seem intrinsic. And finally, we realized we got a very natural way for CTM, and I'll try to describe that later on, how CTM constructs brainish. Okay, and since they're self-generated languages, your CTM's brainish might be very different from my CTM's brainish. And what brainish does is it fuses words, images, sounds, smells, sensations. So for example, a brainish label for a rose might be a fusion of its red color, its sweet smell, its soft touch of its petal. Okay, so as I mentioned, we have a formal uptree competition, a competition for processors to get their information on stage. And so you can think of this a little bit like a tennis tournament. Every processor at each moment in time LTM processor puts a chunk into the leaf of a perfect binary uptree. So they put chunks of information. So we formalize. In the literature, often chunks is a phrase, a word, some very small sentence or whatever. So we formalize the notion of chunk in our model. And so let me tell you what a chunk is. So a chunk is a four-tuple plus auxiliary information. And it starts out with the address of the processor that's putting in the chunk into the competition. And if there are 10 to the seventh processors, that's just a seven-digit number, or 23 or 24 binary number. T is the time the chunk entered. Gist is a very succinct information in brainish, and one can think, because this is a multimodal language, a gist is like a frame in a dream. It might have a picture, a sound, some movement, all of that. But we have to limit the size of gist because we want our computations to be very quick. So this has to be very succinct. The weight is a valence number. So the absolute value of the weight will give its importance, but its valence will also give whether it sees it as a positive or a negative information that it's giving. And the auxiliary information that we generally use is that there's two components. It starts off, intensity will be the absolute value of the weight, and the mood will be just the weight itself. So the mood will have valence. And as the chunk moves up, the competition, as they move up, its first four components will stay the same, but the intensity and mood of the chunk will change, and it will gather more and more information, more and more global information. So when it gets to the top, those last two components will actually have a lot of global information built in as well. So we can see that. So yeah, so before I go ahead, I have to say something very important. We desperately wanted our machine to be totally deterministic. And this is where we had a real problem. If we wanted the competition to have some nice properties and be deterministic, it turned out we had to add so many features to it that it just became so cumbersome that we gave up. And so now our formal competition was forced, actually was forced on us to include a coin flip neuron at each node. So now, from now on, our CTM is probabilistic based on its competition. So we had to add a coin flip neuron, which takes two non-negative numbers in, and it will output A with probably A over A plus B, and B otherwise. Okay, so here let me indicate how the competition will work. Okay, let's see how I'm going with time. Okay, so here, suppose we have A, B, C, D, F, G, H processors. Those are the players that are going in, and they're putting in chunks with absolute value weights 3, 1, 4, 1, 5, 9, 2, 6. And well, let's look at what happens for processor H that's put in a chunk of absolute value 6. Let's sum up that we're calling that initial weight its intensity at that level, and the sum of the intensities at level 31 at the initial level is 31. So we'd like the probability of winning the tournament for each of those processors to be 3 over 31 for A, up to H, which would be 6 over 31. Okay, that's what we ideally would like our competition to do. Okay, so to do that, our probability of H winning with this coin toss algorithm, if we're using the coin toss neuron there, the probability of H winning will be 6 over 6 plus 2 is 8, 6 over 8. And our algorithm is going to be what we call a winner-takes-all algorithm. Whatever gets up there, the intensity will be the sum of the intensities. So whatever wins at that first level, the intensity at the first, for whatever the winner at the first place will be 4, 5, 14, and if H wins, it'll get a new intensity. That's one of the auxiliary variables of 8. And now the probability of H winning, again with the coin toss algorithm, would be 8 over let's see, 8 over 8 plus 14, which is 8 over 22. So that would be the probability of it winning there. And now it's winner takes all. And if H wins, its new intensity would be 22. And now the probability of H winning at this level would be 22 over 22 plus 9. It was 22 over 31. And 31, and if it wins, it will get the sum of the intensities 31. And actually 31, we've been adding from the bottom up. So 31, actually the intensity at that level is the sum of the weights at the initial level. So we look at that. But now let's look at what the probability of H winning the tournament is. Well, at the first level, we see it's 6 over 8 is the probability. And then the next level, it's 8 over 22. And the next level is 22 over 31. And then we get, what do we get? A lot of canceling out again. And we get 6 over 31, which is exactly what we wanted. So we've actually just proved a theorem that the probability of winning depends only on the weight, the absolute value of the weight of the initial chunk over the intensity, where the intensity is the sum of all the initial weights. And in other words, on how the chunk's initial ranking, if you think of the absolute value of weight as like a ranking in tennis, compares with all the other 10 million competitors' ranking. Okay, and we've often asked, well, why not just calculate the probabilities at start? Well, to do that, each processor would need to know the 10 million other weights and their absolute values to compute the intensity. And so the competition is actually doing that very quickly. It's log of the number of processors. So if it's a binary tree with 2 of them, I think 23 or 24 leaves, that would be a height of 23. So pretty quickly, it will compute the sum of the weights. Okay, so from this, we get a very nice corollary from this theorem. Winning is independent of a processor's location, which is exactly what we want. I mean, in the brain, we don't want to have to move processes around every time they're into doing a competition. And if we're going to build such a computer, we don't want to move processes around every time their rankings change or what they're giving. So this is a very nice thing that this competition is independent of the processor's location. Winning the competition is independent of the processor's location. And let's see what the winning chunk looks like. The winning chunk looks like it originally did for the first 4 components. It gives the address, the time, the gist, the weight, and then it has a lot of global information. It has the sum of the initial absolute value weights and the sum of the weights, which we call the mood. Okay, so the well-defined decentralized winner-take-all competition replaces the need for a central executive use in other global workspace theory models. And what we like this is because we see this distributed and fair competition enabling creative participations of unexpected talents, making it a good model for AGI. And what it's doing is, if you have an omnipotent central executive, that executive is not going to know everything about the 10 million processors. If there's a problem to be solved, it's not going to know which one processors has the time or the ability or the interest to even solve that problem. And this will be solved naturally in our distributed system because the one that really wants to solve the problem will put a lot of weight to what it knows or what it wants to do, and it will have a chance of getting into the short-term memory and broadcast to all the processors. Okay, so we see this as a huge advantage of not having a central executive. Okay, so when the winner gets into short-term memory, we call that winner CTM's conscious content. And now we're looking at the broadcast. So as soon as the chunk gets in, it's broadcast to all long-term memory processors, and we call that definition of conscious attention. Conscious attention in CTM is the reception by all long-term memory processors of the global broadcast of CTM's conscious content. So in other words, conscious attention happens as soon as the conscious content is received by all the long-term memory processors. And that gives the processors a lot of information. So as we saw before, the winning chunk looks like this here. So it's going to know the address of the processor that won. We're going to know the gist of what the processor gave. We're going to know the weight that processor gave its chunk, so we can compare that with what we did. We also have the intensity and the mood, which is giving the sums of the absolute value weights and others. And so by dividing that by n, we also know where we fit in by on average in terms of the absolute value of weight we gave, or the mood we gave, just the weight we gave in terms of everybody else. So we get quite a considerable amount of information from the broadcast. Okay, so at this point, we've given some formal model for the global workspace notion. We showed a little bit how this could sort of solve the what's her name problem. This is what we call access consciousness. And we can also see something that we call the Libet effect, which is a little bit like the Libet effect, that there's a delay between when the winning chunk was put in at time t, it took h, which is the height of the tree, to get up into short-term memory and maybe one more tick to get down. So there is a delay between the time the winning chunk got put in by the unconscious processors and then became when CTM paid conscious attention to it. There was a delay here, which happens in our model, and we're calling that the Libet effect. So let me just say a few more words of what's built into the long-term memory processors. When they get these chunks, processors, first of all, store all the chunks they entered ever into the competition. They have a local dictionary. But they also store globally, everybody stores the same one. Processors store all broadcasted chunks. That's the global dictionary. And there are triggers built in. If the broadcasted chunk has a very high absolute value weight, then all processors must inspect that chunk, and I'll get to that definition soon. And if it's very negative, all processors must try to reduce extreme negativity. So here we have some kind of valence built into our machine. It's really going to prefer positive things over negative. And if something is very, very negative, processors are more or less commanded to do something to reduce the negativity. Okay, so now we've talked about STM, LTM, uptree, the downtree broadcast, and links. So as I said before, the processors start out independently, but after a while, we have a Hebbian-like principle, so that processors that have common interests link together. So, for example, the processor that's asked, "What's her name?" when the processor finally gave the correct name, her name was Tina. There will be a bidirectional link formed between those processors. Now, we're doing bidirectional, it's not unidirectional because that's the simplest thing we can do, and it makes things much easier. So our links are always bidirectional. Okay, so when processors have common interests, they start linking together, and that's built in. And what links do is they can transform slow conscious communication which goes through short-term memory, so it takes a bit, not too long, but a little bit, to fast unconscious communication. So when you learn to ride a bike, everything's done consciously, but after a while, riding a bike basically is done unconsciously unless some surprise happens and you have to be very conscious. Okay, so links turn slow conscious communication into fast unconscious communication, where much of the activity is going to happen in CTM. And then finally, I want to say that the CTM is not a brain in isolation. You can think of it as a robot with a CTM brain. You can call it a robot CTM if you like. And so we have inputs coming from the external world through sensors to input processors. And we have outputs going from output processors to actuators that can affect the outside world. Okay, very important for our model that we have. It's not a brain in isolation. And already we can start to see that there is something we call predictive dynamics, cycles of prediction, feedback, and learning. So when processes put chunks into the competition, that's their prediction of what they want or what they think, or when the output processors tell actuators to do something, that's a prediction. When they send information across links, those are kind of predictions. Feedback is coming from the broadcast, from input from the outside world through links, and learning is happening all the time within the long-term memory processors. And one of CTM's internal major goals is to ensure that all its predictions it makes are as accurate as processors. Processors make predictions when they turn raw sensory inputs into chunks. It's a kind of analog to digital conversion. They put chunks into the competition, so digital analog, send information over links, transform chunks into raw outputs. And that's, I guess, the digital to analog conversion, and they get feedback, as I said, from broadcast inputs and through links, and learning correcting happens within the processors themselves. Okay, so we have a kind of lot of things happening because of access consciousness. That's our notion of conscious attention, the beginning model of our CTM. So why would a robot with a CTM brain feel conscious? We had this definition: conscious attention is the reception by all long-term processors of global broadcasts of CTM's winning chunk. And we're going to take as our very first axiom, conscious attention evokes in CTM a unitary experience. Now, this is all, since all processors are getting the same information from the reception, where our axiom is that this is a unitary experience, and we call this our global broadcast axiom. And the reasonableness of our definitions and our axioms, let's look at the first axiom, lie in the number of phenomena associated with consciousness that the model can exhibit or explain easily and naturally, and agrees at a high level with cognitive neuroscience explanations. So we've already talked a little bit about the Libet effect, and what I'm going to talk now is just give you an example like change blindness, but we've looked at other things which I won't talk about, blind sight, inattentional blindness, and other phenomena. Okay, so let's look at change blindness, and you probably have all seen this movie where a detective comes into a room, and he sees a room of a mansion. He sees a dead guy on the floor, and then what happens is he starts interrogating everybody, and he talks to the maid, and she says where she was, and then he talks to the wife, and the wife said she was planting petunias, and of course the detective, who's very astute, immediately says, constable, arrest Lady Smythe, and she says, but why, how do you know? And he says, well, lady, as any horticulturalist would know, you don't plant petunias in this until May or something like that. But for us, actually, the bigger mystery is how come we did not notice the change from the first frame on the right to the final frame on the left. The detective has changed his clothes, and the dead guy has changed his clothes, and now his knees up off the floor. This is the final frame on the left, and the pictures have all changed, and the flowers have changed. And how come we haven't noticed that? So why didn't the CTM, we're posing this to the CTM, or why didn't we see the many changes? Well, the explanation from the CTM is, well, first of all, we noticed that the director was very clever and not showing you the transitions. He was going from the beginning, the one on the right, to interrogating different people. So he was skipping around. Okay, but then the CTM explanation is that there's the same succinct gist that CTM got, that the short-term memory got at the beginning. The scene is the living room of a mansion with butler, maid, and detective, and a man laid out on the floor. And that same succinct gist applies to the first frame and the final frame. So the first frame and the final frame. And that's all the short-term memory could hold at any time when all this other stuff is happening all around. And that's the CTM's explanation. And that turns out to actually be very much like explanations that are given in the neuroscience literature. One thing that it's interesting for the different explanations, they actually use often different aspects of the CTM. So the Libet effect was a delay between the submission to the competition and the broadcast. Change blindness explanation was the limited size of gist in the CTM due to complexity considerations. Gists have to be very small because the chunk has to be very small because the competition going up has to be very fast. Okay, and then blindsight has a different explanation. It's a role played by links if the access to short-term memory is impeded. And intentional blindness had a different explanation when we did it, that the role of weights played a big role in the winning competition. But now we can still say how or will CTM experience subjective feelings like feelings of the smell of the sweet smell of the rose or whatever. So we want to look into that. And here I'm going to say that attention, which we've looked at so far, explains a whole lot, but it's not all you need. Okay. And so what I'm going to do now for this part of the talk is look at the coevolution of brainish and the model of the world. So the model of the world, so that we'll have a model of world processor. It maintains models of the world and of CTM in these worlds. And the model of world processor is widely distributed. And in fact, in our CTM, formally, the model of the world processor is distributed through all processors. Simple, and the model of the world that it constructs is also widely distributed. So the model of the world processors labels sketches in its models of the world with multimodal brainish jits, including labeling sketches or actuators as self, when the CTM consistently detects the actuators carrying out its requests. Okay, so let's give an example. Here we have a little infant who is discovering its left leg. Okay, it can see by power of thought that it can move its left leg, and the its model of the world is labeling its left leg as self. It actually is trying to do its right leg, but it doesn't seem to manage to do that. It's looking over there, but doesn't seem to manage. Okay, so how do we do this formally in our model of the world? So the newborn CTM starts out with a very foggy model of the world. And CTM's very first broadcasted chunk, so we'll have a very first broadcasted chunk. It was a chunk that was inputted by some processor P0 at time 0. It has a nil gist, there's no language yet, and it has some weight W0. There's something that got into short-term memory and got broadcast, okay? And we're going to say, this is its initial sketch. CTM's first broadcasted chunk will be its initial sketch. And in general, sketches will be such broadcasted chunks. And the brainish name of this initial sketch will be the first two components of the sketch. So P00 with the first two components is the name of the broadcasted chunk, PT0, P0 null or nil, W0, that should be nil there. Okay. And brainish words will be such pointers. So remember that when it built into the long-term memory processors, as they were getting broadcasted chunks, they're putting those into their global memory. So they're all having the same thing. So now if they see the word P00, they can just look up in their global memory the the chunk that it points to. And that chunk in general, in this case, it has no information in the gist, but in general, that gist will have information. So we'll point to the meaning of the chunk. So in general, brainish words will be such pointers there. And so we'll call the word PT, and the whole chunk we'll say is the meaning. Yeah, that's in the dictionary, the global dictionary. That's the meaning of the word. So shortly, a primal word for pain will be created. So actually, I given, yes, I failed to tell you, the brainish name P0, we'll call that's the first name of the sketch, the initial sketch, and let's call it blob 0 in English. So that's not in brainish, that will be our English representation of P00. Okay, and now we want to get a primal word for pain. And if you've ever witnessed the birth of a baby, when everybody's really anxious for the baby to cry, and why is that? And then they're very happy when the baby cries. So why is everybody happy? What's going on? Well, the O2, the oxygen gauge, raises its concern for a lack of OT. So there might be, this is like a homeostat, the oxygen gauge, and it's raising its concern for the lack of something it really needs, and submits to the competition a sequence of chunks having negatively valenced weights of increasingly high absolute value. And these chunks win and are broadcast, signaling increasingly desperate scream, do something, do something. So the O2 gauge is saying, do something, do something. But the built-in, all the processors know they must do something, but they don't know what they have to do, so they just do what they do. Their arms and legs flail. The infant pees and poos. The vocal actuator screams and cries. And this last one works. The cry opens the lungs, and the infant takes its first breath. And then the O2 processor lowers its weight because it's gotten what it wants. It's lowered the absolute value of its negative weight. So suppose P1 is the address of the O2 gauge, and at T1 it put in a chunk with very high negative weight, and it's one of the broadcasted chunks. And then we're going to take the word for that chunk, P1, T1, to be the brainish word for the initial word for pain. So it'll be the primal brainish word for pain, and in English we'll call it pain 1. Okay, so we'll now say a brainish gist is a string of brainish words. We're going to say at most 20 because that's something we can manipulate. We don't want too many. We could have it 2. It becomes a little complicated, so we say 20 brainish words. And right now we have our first brainish gist, which is a succinct phrase, P00, and then we're following that by P1, T1. So the first one in English is blob 0, and the second one is pain 1, and that would be our brainish gist, which is saying blob 0 is in pain. And in general, brainish will be a little like this. We'll have the noun in first, and then the adjective secondly. Blob 0 is in pain will be an initial brainish gist. And brainish words and labels continue to evolve and build on earlier ones. So when the CTM becomes a toddler and skins its knee, it will have a label like self, and skin knee pain will be an evolved notion of pain. So we're going to formalize now how to formalize a brainish word may be viewed as a pointer to a broadcasted chunk or nil. So that's what a brainish word is. A brainish gist is a sequence of 20 brainish words. And now I'm going to define a very important notion for us. CTM inspects a broadcasted chunk whenever all processes simultaneously receive the chunk and examine the chunk's content and unpack the words P prime, T prime that appear in the gist. So it's going to look, all the processes are going to look at the gist and unpack the words in it. And unpacking means it's looking at all those words and it's going to its dictionary and it's retrieving the meanings of those words um, in its dictionary. So what unpacking means that in fact, unpacking a word recaptures its meaning, its gist, its weight, and the auxiliary information. Okay. So, thus, inspecting a broadcasted chunks means all processes recapture the meanings of each of the words, P prime, T prime appearing in gist. And now we're having our second axiom, which is really a working axiom here, and we call it the inspection axiom, and we build it up this way. We say it has a primal part. Inspecting a primal broadcasted chunk where the gist is nil evokes a unique primal subjective experience. And the intensity and valence of the evoked experience depends on W, of the weight of that the weight of that chunk. And then the second part is the evolved part of the axiom, inspecting a broadcasted chunk with evolved just G, okay, like skin knee pain, evokes a unique fusion of the subjective experience evoked by the meanings of the words in G. So inspecting means we've had to, as we're building up these words and these experiences, you have to go back into the dictionary and check and understand the meaning and how the meaning was evoked. And the intensity and valence of the evoked experience will depend on W. So we'll succinctly say the working axiom 2, the inspection axiom, is saying that inspecting a broadcasted chunk evokes in CTM a unique subjective experience. The intensity and valence of the evoked experience will depend on W and also some of the auxiliary information. And we're going to define conscious awareness in CTM to arise when CTM pays conscious attention to a chunk, so it's getting conscious attention, but then goes and inspects it, meaning it's retrieving the meanings of all the words in the gist G. And so our axiom, our first axiom, the global broadcast axiom, and our working inspection axiom will mean that conscious awareness in CTM evokes a unique subjective experience, which is unitary based on the broadcast axiom. So that comes from our two axioms here. Now, as CTM becomes consciously aware of more and more broadcasted chunks, the model of the world processor may call attention to this fact with high absolute value weight. The word PT pointing to a broadcasted chunk that calls attention to this becomes a brainish word for consciously aware or simply conscious. The model of the world processor labels the sketch of CTM in the model of the world with the word conscious. And when CTM inspects a broadcasted chunk with the labeled sketch, CTM is conscious. And when it goes in and inspects and retrieves the meaning of these words, CTM will experience, by axiom 1 and 2, a unitary fusion of the subjective experience evoked by this labeled sketch. CTM will feel itself conscious. And this is very much kindred in spirit to Michael Graziano's attention schema theory of consciousness. And it also is kindred in spirit to Dan Dennett's view of consciousness, our notion of CTM viewing itself, the feeling itself that it's conscious. And to really get a better sense of what the model of world is doing, oftentimes looking at pathologies helps. So, for example, the consequences of mislabeling chunks. For example, Cotard syndrome is when a person feels they're dead. So when the CTM has labeled itself dead, it's going to have something like Cotard syndrome. So many people want to get rid of a limb. No doctor, because they don't feel that limb is part of itself. No doctor in the US will do that. But what's happening is that limb is really in its model of the world is labeled not self. So that's how CTM could experience body integrity and identity disorder. And then there's the opposite phenomena, phantom limb syndrome, when somebody's had a limb that's been amputated, but they still feel it itching or the pain. That limb is still labeled self in its model world. And then all sorts of delusional disorders when the CTM, for example, labels its best friend as a spy. And we have some predictions as consequences of mislabeling in the CTM. For example, pain asymbolia is a condition where people don't experience the feeling of pain, and there are different explanations of pain asymbolia. So the usual explanation due to Grayheck is that the pain, for example, the knee is labeled self, but it's not labeled pain. Okay, but another explanation due to Klein is that the knee is not labeled self, but the skin knee pain is there, so people attribute it to someone else's pain. Okay, but Jeren points out that each of these two different explanations has a problem without the possibility that there might be two different kinds of pain asymbolia. And the CTM is actually predicting that, in fact, there could be two different kinds of pain asymbolia, probably more. So let me finally say what the elephant in the room here is. So there are very many theories of consciousness, and how do we align? Well, with the global workspace, we align partly because that's been our inspiration, as I mentioned, Graziano's attention schema theory, predictive processing, the idea of lowering error mistakes. CTM's predictive dynamics is working that way. Embodied, embedded, and active extended mind, well, with sensors, the interaction with the outside world, allowing off-the-shelf processors gives a lot of these features to the CTM. IIT is a theory which is a very mathematical theory, but underlying IIT is that what's very important is feedback and interconnectedness, and there's a measure, and CTM certainly has lots of feedback and interconnectedness. It has high phi. There's the extended reticulothalamic activating system of SOMS. And of course, there's nothing to preclude CTM from having long-term processes that function as ERDAS. And then here's a typical picture that Friston has in many of his papers of the Markov blanket, separating the internal states from the external states. And in fact, if we rotate the CTM around, we can start to see it has exactly a Markov blanket, and it's very evocative. And of course, they're evolutionary theories of consciousness, which are similar in terms, for example, Eva Jablonka says that the global workspace comes from evolution. But the other elephant in the room is the conflict between a number of these theories. So there have been a number of adversarial collaborations, and the first one, adversarial collaborations, was looking at the global workspace theory and IIT, and really just trying to see which one really made sense, because these were loggerheads. And both of these features actually are prominent in the CTM. And people ask, well, how could two theories, which are so different and seem to collide with each other, agree in the CTM? And the reason for that is that the CTM does not align these theories with different components of the CTM. It's just with different functions. So global workspace usually talks about the front of the brain. IIT usually talks about the back of the brain. We don't talk about any part of the brain. We're just talking about global workspace. We're talking about feedback and integration, and those features. The underlying features are all there in the CTM. There's something called key value memory, the paper that came out in June, which was looking at the sort of the similarity between what's happening in transformers and in the brain. And their goal was to connect the dots between conceptualization, memory retrieval, and psychology, neuroscience, machine learning. And central was key value, memory. And they have kind of a map from the words and the meaning, which is very similar to their key addresses, are very similar to our word. Their value content is very similar to our meaning in our evolving brainish language. About 2 years ago, Kevin Mitchell gave 15 multi-questions about what a consciousness should encompass. We've actually looked at the details here, and in terms of the CTM, and you can read about that in our paper. We've gone through that. So our summary and conclusion is that CTM is a simple formal mathematical model of consciousness that is clearly buildable at a high level, exhibits and explains phenomena associated with human consciousness. It aligns with and integrates underlying principles of major theories of consciousness, and it addresses Kevin Mitchell's multi-15 questions, which what should a real theory of consciousness encompass? And so our conclusion is that AI consciousness is inevitable. And you can see our papers. Thank you very much. There they are. Okay, well, thank you. We seem to have 2 minutes more for discussion, or if Manuel wants to add to this. But I know that was a pretty succinct picture of the CTM, but I hope you get the feeling for it. And that we have a preprint up on archive, and we're now finishing up a monograph that should be published within the year, Cambridge University Press. Thank you. Okay.
So the archive, the latest on the CTM is always in the archives.
Right. So that's a preview of our monograph. AI Consciousness is Inevitable is a preview of our monograph, which will really be focusing on the theoretical computer science lens on consciousness and the model, and many, many more details than I have given.